introduction. It's a great pleasure for me to be here today for the second time. And today I'm going to talk about some humidity sensors that we have developed and patented using rose Bengal dye encapsulated plasmonic gold and silver nanoparticles. Just to tell you that these days there is huge demand of various kind of sensors. As we have seen after the COVID pandemic, the sensor technology is exponentially increasing. Everywhere where you go to supermarket or industrial processing, everywhere there are varieties of sensors needed. Now, why we need humidity sensors? One of the reason is that humidity is the enemy for industrial production. For example, cement industry, pharmaceutical industry, electronic packaging industry, electronic chip industry, food packaging industry, all are obsessed with the humidity. So humidity causes huge amount of economic loss every year for this kind of products. So how to monitor humidity or moisture and then protect the product from the humidity? The high performance sensors are needed. One of the kind of sensors that we proposed using this material is optical fiber-based sensor. We use this material as coating elements on the optical fiber and then try to sense the humidity level. It can be inside the car, it can be inside the automobile industry, cement factory, wherever required, this kind of sensor, high performance and tiny sensors that we are using. Now, in this lecture, I'm going to give you very brief overview on nanosensors, then plasmonic nanoparticles as sensing elements. Then we'll talk about the surface plasmon property together with the fluorescence property, how one can exploit them for making the sensors. Then principles of optical sensors, types of fiber optic sensors, and some of the results, important results that we obtain, and we are going forward to do something more in this area. Now, specialty of nanostructured material that we all know, but the most important thing we must know that to get the exotic properties of this kind of material, plasmonic nanomaterial, we need to manipulate their electronic and optical density of states. So electronic and optical density of states is the main factor or the key aspect of using these nanomaterials. Using this electronic density of states, we can surface functionalize the nanoparticles or nanostructure. We can vectorize them. We can use them for different kind of biomedicine. We can use them for many other purposes. So that's the idea of using these plasmonic nanoparticles and manipulating their densities of states for making high performance sensing elements. Now, question is that this kind of technology is very safe, it's economic, and most important thing is eco-friendly. Why it is eco-friendly? Because we know that the sensors use very tiny amount of elements. Now, in the world, if you look at how much electronic gadgets are thrown every year in the landfills, and that causing environmental pollution, the recycled technology is not developed yet. So how we can avoid the damage, or how we can avoid the failure of different electronic devices just through the monitoring of humidity sensor, it is possible. So that's why we are interested in this kind of humidity sensing material. Now, why do we use plasmonic nanomaterials for sensing? There are many reasons. Some of the reasons are using this plasmonic nanomaterial, we can make the size of the device very tiny because we need very little material to have high response. Then we can reduce the power consumption. Of course, power consumption is an issue for every device. We can increase the sensitivity. We can make direct detection, and these are low cost and easy processing. So these are the few reasons for which we use them. And plasmons in metal nanoparticles, for fundamental reason, is known as the Mi resonances. And these Mi resonances we use to exploit the sensing properties of this material. Now the question is, how do we prepare these kind of nanoparticles? Whether the technology would be expensive or cheaper, that is always the question. We should also look at the availability, affordability, and many other aspects of this material. Now, most of the traditional methods that people are using all over the world are the chemical methods. Now, in chemical methods, first we use some precursors, we use some extra chemicals to stabilize them, to coat them, to prepare them, and many other stages are there. Everywhere we use chemicals and chemicals. Well, at the end of the day, we get the desired properties of the nanoparticles, but we pay. The pay is these chemicals are toxic, and when they go at the end of the life cycle of the device, they directly affect our health because they leach into the groundwater. So how to avoid this kind of environmental pollution so that we can prepare these nanoparticles by some other better method? So one of the method people have recently found out is optical based technique called pulse laser ablation in liquid. Now, in this kind of technique, we can use the solid pure target of the material, such as silver, gold, copper, whatever be the nanomaterial we need, even organic material, we can use them. And we directly shine laser pulse on them, fragment the material, and through a mechanism called cavitation bubble and plasma plume generation, these tiny fragments from the target material are disperse into the liquid. Here we can vary the liquid depending on our need. We can vary the pH. We can vary entire kind of laser parameters, wavelength, laser energy, laser fluence, laser pulse duration. That means we have the scope of multi-parameters changes through which we can manipulate the density of states in a customized way. So this is the key, and this is the catch of this game, that we can use pulse laser ablation technique to make this kind of pure nanoparticle, highly nanocrystalline nanoparticle, highly spherical nanoparticles using pulse laser ablation in liquid technique, where optical and electronic densities of states can be manipulated in a wide way. Now, if we use these nanoparticles for different kind of sensing, one of such sensor recently we have noticed, and gold nanoparticles have used heavily into the COVID detection. So just by changing the color of the solution from the nasal or from the throat discharge, if you put them, they change from one color, purple, to blue color, and that is the way we could detect the coronavirus as positive or negative. So these self-aggregations of the gold plasmonic nanoparticles can be used for virus and antibacterial purposes, detection of virus, bacteria, and microbes, protozoa, amoeboids. So people are using all these kind of nanoparticles-based sensors in the swimming pool, in the hotel room, in the hotel bathroom, also in the inside the washing machine, in the hospitals, everywhere we are using these nanoparticles. But using this nanoparticle for making humidity sensor is a quite new idea that we are trying to exploit. Now, gold nanoparticle sensors design is not very difficult. So you have to have very high quality of single mode optical fiber or tapered optical fibers. Then you can use different kind of geometry. The most important thing of this nanoparticle is their localized surface plasmon absorption. And this localized surface plasmon absorption determines the efficiency of the sensor. And these are presently the applications of the kind of sensors we are using various kind of nanoparticles in the optical fiber category. So they are color sensors, gas sensors, large number of sensors are coming up. Every time new sensors are coming up in the market, and they're highly demanding. So for example, temperature sensors for measuring the body temperature, thermal sensors, proximity sensors, movement sensors, accelerometer sensors, infrared detection sensor, pressure, light, ultrasonic, smoke, gas, alcohol, flow and level sensor, humidity sensor, in the defense system, in the warhead, in the space research, everywhere these sensors are becoming important. And plasmonic nanoparticles in this is playing an important role. But the question is, can we further improve the efficiency of the sensing element by putting some extra chemicals, extra ligands, or extra molecules on the surface of this, because surface of these plasmonic materials are very reactive? Can we further enhance their capacity? So one of these is the use of rose Bengal dye that we are trying to use for this kind of sensors. And there are various advantages and disadvantages of these sensors that we can always see. We can see the disadvantages are, in the beginning, the technology may be a little expensive, but when we know how to manipulate them properly, miniaturization of the device and large scale production will make it more cheaper. So there are different types of fiber optic sensors in different types of geometry. We can use fiber Bragg grating. Recently, we used graphene to make some humidity sensor under the fiber Bragg grating geometry. We are also trying to get them in long period fiber grating geometry, tapered optical fiber geometry, and also we can use them in the form of interferometric fiber optic devices. For example, Fabry-Pérot devices. We can use them also fiber optic Mach-Zehnder interferometric devices, Michelson interferometric devices, and also we can use them as Sagnac interferometer devices. So all these optical fiber-based devices, their geometries, their design, their engineerings are slightly different, and there is the challenge. How you can design, how you can vary their geometry, how you can, because they are tiny, so we know that manipulating the things at the tinier level, at the nano level, is always difficult, or at the submicron level is always difficult. And that's where the challenge in the sensing. Otherwise, if we know this very well, then every day, every alternate day, we can discover a sensor. So sensing technology is difficult because of this part of the game. Now, we use the surface plasmon resonance-based fiber optic sensing technology. And in this kind of sensing technology, we use the tapered fiber and then coat the tapered fiber with the nanoparticles, plasmonic nanoparticles that we have prepared in the rose Bengal dye solution. And then we use the standard method, and we sign the optical fiber coated with this sensing element using the tungsten lamp, and then we measure the response using OSA, and that's the way we use the fiber optic based sensors. We make the fiber optics based sensors, and we can also detect the signal in the computer system. Here is the idea of making these sensors and detecting the response of the sensors or sensitivity of the sensor. Look at here. Here is the mechanism, how it works. So understanding the fundamental mechanism of science is the great deal. Once you understand the mechanism, then you know how to manipulate it. Then engineers will come up and they can make the design, and that's the way it will be placed in the market. So starting from the fundamental knowledge to the income generation, there is a long pathway where engineers, scientists need to sit together to figure out how it really works and how it would be worthy, what are the advantages and disadvantages of this kind of sensors and things like that. So this is one of the game of sensing technology. Now look at here, when we make these silver and gold nanoparticles in the rose Bengal dye solution, rose Bengal dye molecule is having kind of benzene ring structures. And in this kind of, you have the amide group and you have the dangling hydrogen. And this amide group and dangling hydrogen and also the carboxylic groups are very much fond of moisture. And H2O molecules can easily be attached with them. The moment H2O molecule will be attached to them, so it will change the chemical environment. This chemical environment will cause electrical signal, and that electrical signal will propagate through the fiber. It would be modulated, and finally it would be detected. Now the question is, the sensitivity of these sensors can be increased by two ways. One, how many number of active sites you can create on the surface of the plasmonic material. And surface of the plasmonic material would be attached to the rose Bengal dye. So rose Bengal dye molecules will donate all these dangling bonds, and these dangling bonds would be the attaching antenna. It will act like an antenna, and the moment water molecule or the moisture or the humidity will fly towards them, it would be immediately attached, and then the signal will be generated, and these signals would be recorded using the transducer systems. And here is the total system, how we connect it to the computer, and then we look at the sensing performance of the sensor. So these sensors are quite useful for various applications inside the, as I told you, inside the car engine, inside the aircraft, inside the industrial processing, microprocessors industry, and electronic packaging industry, where the chips are packaged. High vacuum is needed for that, and high vacuum, always the expensive process for the most of the electronic industry, cement industry. Pharmaceutical products get damaged because of the moisture attack and the humidity attack, where you can closely monitor the humidity and can avoid the loss. Here is some of the applications of these sensors also used for monitoring the glucose in the diabetic patients. We are also working in the same area for some reason. Now, there are a lot of applications, as I said, because in detail, if I go into very much technicality, it will take a long time. However, I will show some of the important results that we have got, and based on that, we received the patent. So it has application in the military and law enforcement, image capturing. People are using this kind of sensors, image processing, feature extraction process, feature comparison process, biometric identification, partial discharge detections in the power station, which is a very damaging power cut often happens for this kind of moisture attack in the transformer system. So there the detection is very, very important, and on-time sensing is very important. And then airborne laser optics, these kind of sensors can be used. So humidity is everywhere. We cannot avoid, because Earth is on water. So humidity, and also in the earlier lecture, it is said that the water molecule is one of the very damaging things for various kind of corrosion process, various kind of contamination. So we need to protect the system from water or molecule corrosion. So here is basically the kind of nanoparticles that we use in rose Bengal dye. So we use different laser fluents, and out of many laser fluents, many sample we prepare. I will be just showing you the optimum fluents that we got the best nanoparticle, 11.49 joules per centimeter square. In this kind of fluents, we got silver, gold, rose Bengal dye encapsulated particles, and these particles are used to taper the fiber, and then finally we coat the fiber with this kind of colloidal suspension of nanoparticles. And these fibers are used for the sensing purposes of humidity, water. But before we go through the sensing, we also put a PVA layer, polyvinyl alcohol layer, to enhance the probability of attachment of these molecules. And we have found that the layer of PVA molecule works very nicely, and we can really use them for the high performance detection system. Here I am going to show some of the results from our work, that for this kind of nanoparticle, first we need to characterize. After the production of this nanoparticle, we need to characterize them. So what are the characterizations required? All basic characterizations. For example, we have to characterize the structure, morphology, optical properties, electronic structure properties, because as I told you that the electronic structure properties will give you the electronic density of states, that will also decide the densities of states. So both manipulation of the optical and customizations of these densities of states require such measurement. So we first make the absorption measurements and look at where the localized surface plasmon absorption is maximum. And we use these maximum localized surface plasmon absorption peak to make the sensing element. And then we have to also look at the transmittance of these kind of material, because if it is not fully transmitted, then we can see that we will not be able to propagate the signal. So both transmittance and absorption measurements are necessary for this kind of material. And then we look at what is the best material that we can get in terms of their fluorescence quantum yield. Remember, two properties we are using here. One property we are using fluorescence quantum yield, how much fluorescence is there. Second property we are using plasmon absorption. So that this is a new technology which is coming up for the sensors called fluorescence plasmonic technology. This is very recent and very new. So here, to look at what is the kind of fluorescence you get and what exactly the wavelength at which the fluorescence is happening, we need to look at the color chromaticity map and color temperature, which is called CIE 1931 color purity plot. In the color purity plot, we see that these nanoparticles are exactly in the purple and violet region, which is the strong part of the region where we can make them very useful for the sensing purpose. And we also calculate the fluorescence quantum yield from some theoretical formula and then match with the experimental results. And here are the samples that we have tried with. So you can see we have tried with various laser fluences, and then we looked at their absorption peak, fluorescence peak, absorption color purity, fluorescence color purity, and most important thing, fluorescence quantum yield. And fluorescence quantum yield can go as high as 0.3 at the laser fluence of this. However, at laser fluence of 11.94, although the fluorescence quantum yield is slightly lower, but there are many other things which is better. So here is the trade-off, how we can compromise between the plasmonic property and the fluorescence quantum yield property to get the best action in the sensing technology. So here is the measurement process of the sensors, because this is very long discussion. So if anyone is interested, we can discuss afterward how to make them and how to really exploit them for the measurement. And here is the mechanism of the rose Bengal dye-encapsulated silver gold nanoparticles together, because we know silver has a very sharp surface plasmon, gold is having, but gold is having lower surface plasmon than silver, but gold has stability. Gold is non-reactive and inert, and silver is little reactive to the oxygen. So we therefore make a kind of core cell nanostructure so that we can exploit the silver plasmon and we can protect silver from the oxidation process through the gold. So silver gold core cell nanostructure is very important, and here is really the intelligent technology is required for the kind of production of the sensing elements. So here is the measurement. When we look at the relative humidity, so we use this sensor, then exposed to the varying concentration of humidity. We start with 40% humidity and we go up to 100% humidity. If you look at the humidity level in most of the industrial processing, that is nearly between 40 to 50%, and below which it's very, very difficult to control. You need high vacuum system, and most of the food packaging, most of the other packaging does not require high vacuum. Therefore, there will be always the humidity level. Now, how to improve and how to detect the humidity, that is one of the questions. So we started with variable humidity level and look at the response of the transducers in the optical fiber geometry. And as you can see here, that the rose Bengal DyeEncapsulated silver nanoparticle, which is shown here by yellow, and then gold nanoparticle, which is shown here by blue, they are having very high sensing performance. And then when we make the optical fiber and then coat, and then we look at the silver gold rose Bengal dye at different fluence, last three lines in this plot, you can see the sensing quality or the sensing response improved remarkably, and therefore we can use these kind of material for high performance sensors for the humidity detection in the future. So here is the relative humidity sensors and transducers. We have proposed that the PVA coated silver gold rose Bengal dye encapsulated nanoparticles prepared at 5.97 joules per centimeter square fluence have the highest R squared value, which is 0.9691, and it has a sensitivity of almost like 1.1587, and this is really higher compared to the existing humidity sensors made of traditional materials or some materials made of chemical root. Here, remember, even if we get little lower sensitivity but less chemicals, because pulse laser ablation technique does not require any extra chemicals or precursors. So in that way, it is very environmental friendly, and we can get very high quality nanoparticles. So that's the purpose of making this kind of sensor. And it is, again, the intensity level of these kind of sensors as a function of wavelength. And we see there is a very strong sensitivity at the wavelength of 850 nanometer. That means at the infrared range. So in conclusion, we just would like to say that realization of practical, low-cost, and high-sensitive fiber-optic humidity sensors is a new type of plasmonic sensor which can open up new avenues. And a lot of people in the world are working now after in last 2-3 years. This technology is not very new, particularly combining the fluorescence with plasmonic is a kind of new technology. So this new type of nanoplasmonics-based material as sensing coating agents can be prepared by PLAL technique. And I told you, because the PLAL technique has a lot of parameter space, so therefore customization of the electronic and optical densities of states are possible in a wide range of system, where you can play with the morphology, you can play with the shape, you can play with the geometry of the nanoparticle, pH, laser energy, laser pulse duration, many other things. So optical, physical, chemical structures and humidity sensing properties of these coating materials can be outstanding. And high sensitiveness of this rose Bengal dye coated nanoparticle. Rose Bengal dye is a very interesting material, and a lot of work has been started with this kind of dye molecules. This dye molecule is a very, very promising for sensing technology. And we can really get very high sensing performance using rose Bengal dye in combination with polyvinyl alcohol layer. As I told you, a lot of ligands, a lot of surface passivated states, if you can create, better would be the humidity sensing. It's all about the surface chemistry. It's all about the surface reactivity, where electronic densities of states, optical densities of states play the important role. That's the fundamental physics, that's the fundamental science we must understand. So in acknowledgement of, obviously, I would like to thank Dr. Manjit Singh and Dr. Manjit Singh Goyal both for their continuous communication with me, and I'm thankful to them for inviting me again. And also UTM and Ministry of Higher Education in Malaysia, for various grants they are providing us to continue this work. And our research group, Dr. Safwan, Dr. Hazri Bakhtiar, and one postdoc student is an excellent student, Dr. Ali Akil, who is working main workforce in this area. Department of Physics and Ibn Sina Institute of Scientific and Industrial Research, we have a nano science center where most of these equipments are there. We characterize in that particular, and we have also central instrumentation centers. We call it UPMU, and they are providing all the facilities for this kind of research. And that's the way our research is going on. Anyone interested, we can always collaborate with them. And thank you so much for your patience. And if you have any questions, it's open for you.